All right, so I'm going to present some updates to the PEXSI library and some results on another solver I'm working on for sparse symmetric matrices. So let's start with some motivation. We need to handle sparse matrices because, first of all, they arise in many applications, and I mean, some methods require sparse factorization, which is one of my key topic of interest. And as you all know, some other require some inverse elements. So what's the challenge on modern platform? We have a rather modest amount of memory per core. The communication costs are getting relatively high compared to the computation costs. And also on large parallel platforms, distributed memory platform, we can observe large performance variations. So we have to have these three things in mind when implementing our algorithms. Okay, so let's start with the parallel selected inversion available in PEXSI. So many applications in, for instance, in electronic structure theory require some elements of an inverse matrix. And so that's the purpose of the selected inversion. I will just skip through that. So the naive solution was to, compute a sequence of a triangular solve on columns of the identity matrix. And of course, this is pretty inefficient. And so there are better algorithms. And selected inversion is one of them. We are computing the entries of inverse corresponding to the sparsity pattern of the original sparse matrix A. And so, okay, I'm going to skip that. So what's the data layout in the selected inversion implementation available in PEXSI? It's basically a 2D block cyclic layout based on supernode sizes. So you see that the block sizes are not uniform because they correspond actually to the supernode size. There is no explicit load balancing of the non-zero per processor, but this type of layout has been shown to work well in practice. So this is basically the layout we are using in PEXSI. So now, how do we compute a supernode? So in the implementation of the selected inversion, we have basically two levels of parallelism. So here I'm not talking about a hybrid parallelism. I'm really talking about algorithmic level. So we are exploiting parallelism when processing a single supernode, and we are also exploiting concurrency between supernodes. So let's first review how a single supernode can be processed in parallel. So in this example, we are looking at the computation of supernode 6 here. And so the first thing is that the selected inversion algorithm corresponds roughly to let's say, a traversal of the elimination tree of the sparse matrix in the opposite direction as for the factorization, meaning that a factorization is a bottom-up traversal of the elimination tree, whereas the selected inversion is a top-down, which in this example means that supernode 6 corresponds to requires the values of supernodes 8 and 10 to have been computed before. So these we refer to these values as S inverse, as shown in this equation here, and in this red area on the figure. They correspond, these entries correspond to the ancestors in the elimination tree. And so the way we are parallelizing the work in selected inversion is that the processors owning the ancestors, so owning the blocks in this red square, will be responsible for computing the contributions from these ancestors to the current supernode we're processing. Then the next step is to reduce all of these contributions. And so since, in most of the time we are dealing with symmetric matrices, if we were to exploit that symmetry, the communication pattern would have been like complex, as shown here. So in the first implementation of the parallel selected inversion, we decided to simplify this by simply overwriting, by using basically non-symmetric storage, which is we were overwriting the upper triangular part of the matrix by the transpose of the lower triangular part. So by sending to cross-diagonal processors, and as a result, that allowed us to do communication only within rows and columns of processors. So we were in this example broadcasting blocks from supernode 6. I mean, in each column 8 and 10, like this. And then the reductions were done along the rows of processors. So, like I said, this was the original implementation, and we did that because the communication pattern was kind of complex. So, but recently we've been trying to integrate PEXSI with symmetric solvers. Whereas in the past we were systematically using SuperALU, which is non-symmetric. So as a result, we do not necessarily have the upper triangular part of the matrix allocated. And so it might be interesting to forget about this simplification of the communication pattern and do the complex communication pattern. So that's what we've been doing lately. So how does it work when we only have the lower triangular part of the matrix allocated? So first step is to broadcast the blocks of supernode 6 to the appropriate processor. So when I say appropriate processor, it's just that you are going to broadcast along the row until you reach the diagonal, and then you're gonna somehow like continue broadcasting to the processor in the column corresponding to the diagonal block. So for block, this red block owned by P12, sorry, it's gonna go to P11 and P5, whereas the block owned by P6 is gonna go to P5 and P4. So in terms of computations, there is a difference between this algorithm and the previous one, in a sense that the number of updates computed by a processor the number of contribution is going to be different. So the processors owning diagonal, the blocks of S inverse on the diagonal, which is in that case P11 and P4, are computing only one contribution. Whereas, sorry, and what I'm trying to show is that those contributions, since all the communications are performed asynchronously, will be computed as soon as possible. So for instance, let's assume that the first broadcast, broadcast sent by P12 is happening before the broadcast sent by P6. So that means that P11 will get, for instance, the block before, and will be able to compute its contribution as soon as possible while the other broadcast is happening. So when the broadcast from P6 happens, then P4 is also able to compute its contribution, and P5 is able to compute its contribution. Now, the difference with the algorithm from before is that P5 has actually two contributions to compute. So it has the contribution that is going to be reduced in P6, and also the contribution that is going to be reduced in P12. So I'll just keep over the details, but it's about like just a bunch of transpose. And okay. So after those contributions have been computed, then they are reduced to the corresponding processors. And then the processors in the current supernode column will compute their update to the diagonal block, which would be ultimately reduced. So as you have seen, the main difference is the complexity of the communication pattern. But you may have noted that the computational load is now not as balanced as before, because some processors are responsible for computing 2 updates instead of 1. And the other thing, which is not really apparent in that example, is that the messages tend to be a bit smaller than in the other approach. But we'll see how performance is impacted by that. Okay, so here's the first run of experiment performed on Nurse Corey. So 4 GB of memory per core, 32 cores per node. We are looking at the Haswell partition, and we are using Parmetis for the matrix ordering. SuperALU-Dist, the last version 5.1.3. And we are looking still at flat MPI implementation in those experiments. So again, really the idea of the implementation of a parallel selected inversion is to focus on how to pipeline computations and overlap with communication as much as possible. All right, so I have this example where I'm comparing the let's say the current implementation of the selected inversion, which uses unsymmetric storage, to the upcoming implementation using symmetric storage on a 3D lithium case. So here the factorization time is given, as a reference. And as you can see, both, so first of all, for this particular type of matrix, so 3D problems, the amount of work per processor seems to be, is a lot higher than in other types of problems. And so as a result, the load imbalance that I have told you about in the slide before doesn't really impact the processing time, because all the processors are kept busy throughout the selected inversion. The nice thing here is that the finer granularity, because now our computations are really block-based, and higher asynchrony that we were able to express in the algorithm allows the performance to be even higher than what we used to have. So just so you know, I don't have the plot, but I did similar experiments on the other extreme, which are like 1D problems. And in those problems, apparently my preliminary results indicate that the unsymmetric storage in that case is better. But that's, again, because now we are paying a higher price for load imbalance. All right. Now, we're talking about unsymmetric storage versus symmetric storage. So what's the impact on the maximum memory usage? So in all those experiments, I've been using a non-symmetric factorization. So the impact is actually going to be lower than what it would have been on with a symmetric factorization. So I will need to work a bit more on this. But basically, what we can see here is that so what's displayed on this plot is the ratio between the maximum memory usage of the selected inversion using unsymmetric storage divided by the maximum memory usage of the selected inversion using symmetric storage. And so roughly we have like a ratio of 1.4 in average. So meaning that for this particular case, we are saving around like 30%. So this is, I mean, this is a good result though, because that means that for a particular platform size, you could run larger problems. All right, so that's what I have on this symmetric storage thing. Now the next topic I'd like to bring up, since we've been talking about hybrid parallelization in the previous talk, I want to point out that we are working on OpenMP parallelization and as a proxy, first of all, for a hybrid OpenMP implementation. So as a first step, we've been looking at shared memory platforms only, and we've been looking at the types of algorithms. So as you probably all know, there are like many ways to perform a factorization, and the most well-known way are left-looking and right-looking. And so right-looking has good properties for parallel systems. So we were just wondering whether there was like a similar thing for selected inversion. So there is like, you could express the algorithm to be either left-looking or right-looking. What's, again, since the selected inversion is a top-down traversal of the elimination tree, it's like the opposite of the factorization, or the mirror of it. So basically, the left-looking factorization corresponds to a right-looking selected inversion in terms of sequence of operation, whereas the right-looking factorization corresponds to a left-looking selected inversion. So since right-looking factorization seemed to be the most promising parallel algorithm, we've been looking at how we could express a left-looking selected inversion. So like I said, the algorithm basically determines the order in which the updates are computed. We've been looking at task approach using OpenMP tasks. And so in terms of operation, left-looking roughly has two types of operation: outer product and inner product. So I just like skim through this very quick. So since it's a left-looking algorithm, so this part of the matrix here has already been computed. Supernode K is the supernode that has just been that is currently being computed. It has just been inverted, and so as a result, you need to update the entries to the left of it. So there is like a outer products task which corresponds to these blocks. So the corresponding rows of the current supernode will update blocks having non-zero entries to the left of it. Then there is also inner products, so corresponding to the entries here in the upper triangular part. But again, let's first look at the performance rather than dig into the algorithm, because it's a bit hard to follow. So here, what I'm plotting is the scalability, the speed up achieved by this left-looking selected inversion on a collection of electronic structure matrices on Corey Haswell. So each processor, I mean, a processor has 16 cores. So as you can see, we can achieve like a pretty good speed up on those matrices. And if we compare the average speed up achieved by this left-looking selected inversion to the similar implementation of the original selected inversion algorithm, which is right-looking, you see that the average speed up is actually higher. So meaning that this algorithm scales better. Now on KNL, we observe a similar trend. We can like scale up to 64 cores, like on some matrices, on some problems, achieving speed ups more than 20. I have to point the fact that the two matrices here, DGDFT graphene 180 and CS time was 2. They do not scale as well, and the reason is that the amount of work in these two problems is simply too low to keep all the cores busy. If we look at the average speed up, we have even like better average speed up compared to the right-looking algorithm. So all in all, this is very promising, and we are going to look at how now we can transform this algorithm, this shared memory algorithm, into a distributed hybrid memory. Hybrid parallel algorithm. All right, and so finally, I'm going to talk about a solver for symmetric matrices that we are currently, that has been integrated to the PEXSI package, interfaced with the PEXSI package, so that in memory constrained environment, one can use a storage optimal solver when dealing with symmetric matrices. So the key feature of that solver is that it's implementing a fan both method. So what is it? It's just that for a basic Cholesky algorithm, there are many ways to compute a factorization. Roughly, there are like 3 types of operations involved. First, for each column, you're going to factor it. Then you're going to update the next columns, and in a parallel setting, it's often interesting to aggregate updates into a temporary buffer and send them only once. So we have this factor, update, and aggregate. So there are, like in the literature, the algorithms, Cholesky factorizations algorithm have been classified into 3 families. The Fanin family, where so that would, in a Fanin algorithm, what you're doing is that the processor which factors a given column is going to compute all the updates for the next column and put that into aggregate vectors, and then send those updates. In a fan-out algorithm, which is what most people are familiar with, once a column has been factored, the factored column is sent to the columns that need to be updated, and the processor owning those columns are the one computing the updates. And finally, so the family is determined by the type of data exchange, and also the type of and where the updates are performed. And so there is basically a super family to these two, in which algorithms will both use aggregate vectors and directly compute updates. All right, so the Cholesky factorization algorithm available in symPACK is a fan both algorithm, meaning that you can choose. We can choose basically wherever the updates need to be computed. The design philosophy is the following. We try to remove all the synchronization points. As in the parallel selected inversion, we are using asynchronous point-to-point sends and no collective calls because we want to exploit full asynchrony. We want also to minimize the memory, the number of memory operations. So by using the appropriate layout, we can avoid to make extra copies when sending data, meaning that we don't have to pack it. symPACK uses a task scheduling mechanism in a sense that the tasks mapped onto each processor are determined statically, but the order on which they will be processed is determined by the order in which you're receiving the data. So we have like a mechanism where we have a local task queue and a ready task queue. So local task queue will contain all the tasks that you're supposed to do. And based on whatever you're going to be receiving, you're going to update dependency counts corresponding to a certain task. Once a task has reached a dependency count of 0, that means that all the incoming dependencies have been satisfied. So you can move that task to the ready task queue. And the ready task queue is just like processed with some policy. You just pick a task. You know that all the dependencies have been satisfied. You pick that task, you execute it. That task may communicate, so may update task on remote processors by sending a message, or update local task by updating their dependency count. So the idea here is that we exploit asynchrony through this management of this ready task queue. There are many ways to pick which task you're gonna process. And as an update in the upcoming version of symPACK, the ready task queue here is going to be processed, will be potentially processed by multiple threads. Right now, symPACK is also pure MPI, but the next implementation is going to be hybrid. And so the threading is achieved by selecting tasks in this queue using multiple threads. All right, so in terms of strong scalability, we did, so these experiments were performed on Edison, actually, and we have been comparing symPACK to different state-of-the-art solvers. So SuperLU dist here is just given as a reference because it's not a symmetric solver. So of course the number of flops performed by SuperLU is twice as high as the other solvers. And what we can see here is that I mean, on this particular problem, we can outperform PASTIX and MUMS for the Cholesky factorization. I have another example where if we consider a pure flat MPI codes, we see a similar trend. But PASTIX has the ability to exploit hybrid parallelism. And so if you turn on hybrid parallelism for this particular problem, then it's able to outperform our flat MPI solver. I have to just point the fact that it's not true for all problems. So sometimes hybrid parallelism is helpful, sometimes it's not. And I just picked that problem because I think it's interesting because it's a problem where threading actually helps. All right. So this is like a motivation for us to do this hybrid parallelization also for symPACK. Okay, so we have seen that we have a storage optimal selective inversion algorithm now, and that pipelining and an asynchronous task execution model are critical for performance on distributed memory platform. PCLin is available in the PEXSI library. We are looking at scalable shared memory implementation of the selective inversion as a proxy for future hybrid implementation. This will be available in a future release. And also, I invite you to try out this symPACK solver, which is going to be interfaced with PEXSI in the next release. Thank you all.